Good afternoon, everyone, and welcome to our technical talk event on network access quantities, AMO summary and lesson learned. I'm Tara Meir, Principal Planning Engineer at Western Power, and also IEEE PES PLS Chapter Chair in WA. Tonight, on behalf of WA Chapter, I would like to thank you all for attending this event, and I would also like to thank our speaker, Lucas Zieland, for scheduling some time for this event and sharing their experience with us. Before I go through the bio and everything else, I'd like to ask Dean Sharafi to talk a little bit and share a bit about IEEE Power and Energy Society.
Thank you very much, Tara, and thanks everyone for attending this evening session. I'm sure it will be a very informative session. I just ask by show of hands how many IEEE members are here? Okay, 4, 5, 7. All right, we can do better. So if you're here and you like this session and you think it adds value, you only need to see me if you want to join IEEE PES. And I think it will be very worthwhile. I'll show you what I mean here. So IEEE is the largest engineering organization in the world with about 500,000 people globally. And Power and Energy Society is one of the 39 societies. So there are other 38 societies that form IEEE. And IEEE is producing more than 50% of the standards in the industry. So that is how important it is. But PES, globally, we have about 40,000 members. So we are in different regions of the world, and this region is region 10. So highlighted over there, which covers a big chunk of the world, Australia, New Zealand, and China, goes all the way to Japan and on the east to Pakistan. So in terms of publications, IEEE PES have a lot of very useful publications. I really like the IEEE Power and Energy magazine, and if you have seen it, you know what sort of value it produces for us, especially in this very rapid energy transition era, and it focuses on really very prominent and important things. So if you haven't seen it, I would recommend that you grab an issue of the magazine and see for yourself what I'm talking about. So other than publications, so there is also the Electrification magazine, which is a digital magazine, and there is a Spanish version of Power and Energy Society magazine. I should also say there are a lot of conferences that IEEE PES organizes. For this region, there are 4 conferences every year. So the next one, if you haven't been to Kathmandu, Nepal, the next one will be in Kathmandu in November, and then after that in Bangalore in India. And I guarantee if you participate in those conferences, you will enjoy all the presentations and the value that you get from that. So after this, after my sales speech, I give it back to Tara to introduce our speaker. Thank you.
Excellent. All right, thanks everyone. It's my pleasure to introduce our speaker for tonight's talk, Mr. Lucas Zieland. Lucas is an electrical engineer with over 10 years experience in a broad range of fields, including power system planning, operations, control systems, and larger scale project delivery. Lucas is passionate about supporting the ongoing energy transition, having been involved in a smaller scale project, in addition to greater scale planning, whole of system plan, electricity statement of opportunities and operations, outage coordination, constraint development. Lucas's recent work with AMO has focused on the WEM reform program, working to operationalize the security constrained economic dispatch, which we know as SCED, and plenty, I would say. Tonight, Lucas will be sharing their insight and experience on network access quantities, and we have allocated half an hour at the end of the session for Q&A. Over to you.
Right, yeah, that's a lot of people here. Thank you very much for taking the time. And yeah, so we're here to talk about network access quantities. The very first thing, let's start with all the presentations, acknowledge the traditional owners of the country throughout Australia and the land that we're on here to the lands of the Whadjuk Noongar Nation and recognise their continuing connection to land, waters and culture. We pay respect to their elders past, present and emerging. And also, despite this being an AEMO branded template, me being a principal engineer at AEMO, the opinions expressed herein are those of the presenter, me only, and are not necessarily the opinions of AEMO, and a lot of other disclaimer stuff here about it not being legal advice that I encourage you to read. All right, so today, in order to prepare for talking about network access quantities, which will be most of the time, I'm going to give some background on capacity mechanisms in general, which aren't necessarily a unique thing to WA, even though we've had one for quite a long time, and some background on network constraints as well, which are pretty commonplace over east, but relatively new here in the west, and so somewhat of a black magic art to some electrical engineers. Network access quantity being the merger of those two things, really. That's all it is. It's not a complicated concept, but the devil's always in the detail. Finally, I'll present on some of the things that we've learnt from having run this for 2.5 years, and some of the issues that we're working towards fixing over time before, half an hour of questions if you've got that many for me at the end. So, capacity mechanisms. The big question that any capacity mechanism is seeking to confirm is that we will have enough generation during our time of most need. That's what we want to know. We can just add all the generators together, but there's obviously a lot of nuance to that. We want to know that we have enough generation during our time of most need. You don't need a reserve capacity mechanism to do that. Obviously there are lots of parts of the world, including the East Coast, that don't have one at all. But why might you want one? For example, if your load is peaky or uncertain, or is the energy market difficult to model and predict as a result of that. I have a little chart here that's used in quite a lot of AEMO presentations. The purple line's the WEM, the red line's the NEM. And for 10% of the time, there's about 30-something% of generators that are only used in that 10% of the time. And as you go to smaller percentage of times, there's a lot of generation that's only used a very small amount of time. A lot more than, say, the WEM, where there's only 20% of generation that's only used 10% of the time. The problem with this is that if those peak events don't happen in a given year, then that generator has almost no revenue and might not be able to continue functioning. So one reason to have a capacity mechanism is to de-risk that, to provide insurance and give a constant stream of revenue to generators that only needed during those peak events, of which we have quite a peaky grid, so it's quite relevant to us. Another thing, another reason that you might want to talk about capacity mechanisms is how good is your plan B? As you might know, us here in the Swiss have quite a geographically isolated grid. We don't have interconnectors to another system, so we can't borrow power if something goes wrong. So we have to be quite self-sufficient. So another reason to have a reserve capacity mechanism is to ensure that you are self-sufficient and you can handle all the cases that you want to handle. You don't need a reserve capacity mechanism to handle outage scheduling, but if you have a nice strong capacity mechanism that enforces outage scheduling and makes it so people have penalties or incentives to do it correctly, then you have a much easier time making sure that your generators are available in those times of need when you might need them most. So that's capacity mechanisms in general. One concept I'll introduce here is this idea of a capacity credit or maybe a certified reserve capacity. But the idea is just because you have nameplate capacity doesn't mean you can rely on them for that at all in your time of most need. So we're just trying to convert what we do know about a facility into this idea of how much can we rely on in our time of most need. And that's true of capacity mechanisms before network access quantities. So for a coal and gas facility, perhaps, generally pretty close to their nameplate rating is what you can get at your time of most need. You might have to think about whether or not they're going to get derated due to high temperatures. You might have to think about whether or not they have fuel shortages for any particular reason, but generally pretty high capacity credit to nameplate rating ratio. For non-scheduled facilities, wind, solar, things that rely on things that you don't control, you need a way to assign capacity credits to them. The way we do it in the WEM, in the Swiss, is to consider a concept of relevant level, which is just fancy word for saying how much did we get from you in our time of need historically, or if we're looking at a future facility, if we've got a wind forecast or historical wind data for the site, we can make a similar kind of judgment. How much do we get on average during time of need? And the hopes is if you have quite a lot of them, then on average you'll get that when you need it. The other category here, which is a bit more difficult to assign capacity credits to, is some kind of storage facility, because obviously there's a limit of how much you can use them. This here, I've pilfered from a lovely slide from one of my colleagues, Toby. The line here is the load profile, just the general load profile. It doesn't necessarily need to be the Swiss, but this one is on a peak day that we had. And the purple bit is a hypothetical contribution from batteries during a peak event in some forecast scenario. In this kind of world, if we've only got 400 megawatts of capacity credits of battery, and you have 4 hours of storage, which is what our rules currently require, just convenient, then you haven't got a problem. You've got enough battery there to get through that peak and cut it sufficiently. But if you had 1,200 megawatts of batteries, which might be the future if people are building lots of batteries, you don't necessarily have the energy you need to fill these bits, so we have a shortfall. So this is the idea of how do you assign capacity credits if how much their value is depends on how much of it you have. Really difficult thing that we're working towards. But the idea is change this threshold of how long you need to provide capacity credits, and you get a number for capacity credits, which is what we're doing now. And overall, if we take our capacity mechanism pre-network access quantities, looks like this. This diagram I've stolen from a capacity credit mechanism presentation that our WACME team loves to present. The idea is that it generally comes down into 4 parts, and I'm oversimplifying this, there's lots of nuance, but the idea is you start with forecasting how much generation you need, you do a bottom-up approach or a top-down approach to how much load there is and how much losses there are, how much do you need. The second step is doing something to calculate these capacity credits I was just talking about, however you do that. The third bit is assigning how much each load needs. So what were they requiring during our historic times of need is the idea of how much capacity credits the load needs. Once those two things are married up and you have enough, the last step is just monitoring that everyone's doing the right thing and being a police officer, imposing penalties and enforcing that the mechanism works properly. Now, the other thing here is that if you don't have enough generators applying, there's a whole world here of backup plans. We have something called the Supplementary Reserve Capacity Mechanism and the the Non-Co-Optimized Essential System Services, 5-letter acronym, really good. But the idea is there a backup plan if you don't have enough? Can you go to the market? Can you get an interconnector or however else you do it? But the idea is our mechanism has these two, which just says, if you're not in the mechanism but you're a generator, you're better than nothing. Please help us out. That's capacity mechanisms in general. I'm going to move a little bit to constraints in general. My colleague Dean has asked me to pretty please present this without a single reference to formulas, so hopefully that makes for an engaging presentation for you. Because constraint equations in general can get very numbery, very symbol-y, and not particularly easy to understand if you're not in the field. So, the first concept I wanted to introduce to you is the concept of a limit. This is what my friends at Western Power will be very familiar with, and it's just advice that you can't do something to the network, some limit. We don't even necessarily need to know why as part of a network access quantity model, just that it is the requirement. And I generally categorize these into 3 kinds of limits. I'm sure they do as well. We have thermal limits, of which one kind is hard thermal limits. Basically, if you go over this limit that you've been told the thing's damaged, it's going to start a fire or it just breaks and you can't use it for the rest of summer, which is not good. Hard thermal limit. Second kind I'll introduce is a temperature dependent thermal limit, soft thermal limit, whatever you want to call it. But the idea is there's lots of equipment that can provide more or less capacity depending on system conditions. So for example, we have a transmission line, excuse my crude paint drawing, but we have a cold line is shorter and a hot line is longer, and it sags more. And when it sags more, it's more likely to touch a tree or the floor or a car that's driving underneath it and cause some damage. So we have some kind of limit about how much clearance we need, which means we have some kind of temperature limit, and depending on what assumptions you make, you get a limit for the transmission line that you're talking about. The third kind, which is a whole world in and of itself, which I won't touch do nearly enough justice, is this idea of non-thermal limits. Luckily, we don't have too much of those here in the Swiss. We have a relatively strong network and a lot of stable generators, but in future, these are going to become more of the problem than they are now. And these are things that relate to rule requirements and things that aren't necessarily temperature it will break type issues. So whether or not the voltage is within the technical rules or whatever voltage target that you have. Whether or not facilities, if they're on at the same time, will oscillate with each other and cause some kind of damage, which there's a whole field of research in. So all these kinds of requirements fall into the category of non-thermal limits. The second concept is this idea of constraint equations, which I'm not putting any symbols up here. The core concept here is that in WEMD, as a market operator, generally we can't dispatch for temperature. We can't say keep this thing less than 90 degrees because our computer can't handle it, doesn't have a way to do it. It can't dispatch for voltage, it can't dispatch for flow on a line, even if we knew what that limit was. The only thing we can do is dispatch the active power of a facility. We can say you are doing this many megawatts, and maybe we have some influence on the megavars. So that's where constraint equations come in. We're trying to convert those limits I just talked about into something that we have control over. The megawatt dispatch of a facility. So how do we do that? There's two things I'm going to introduce that pull that together without putting any constraint equations. The first is this idea of sensitivity. And sensitivity and coefficient, lots of words that you might use for this, but just a conversion between what a generator is doing and what the network is doing. That's all that means. It's not that complicated. Here is a little bit of the Swiss that I took out of this document here, so it's public knowledge, I've got to be very careful. And if we have this region of the Swiss, we might do some studies and try and figure out what could breach a limit during some kind of study. For example, one of the equations we made in our first network access quantity model was that if that line there that I'm pointed to with a lightning bolt that's purple trips, gets a freak tornado, lightning strike, somebody drives into a pole, something happens, then this one will get overloaded. That's the constraint equation that we built. And the idea of sensitivity is to think about what every generator or every load was doing in isolation and how they contribute to that problem. So if we had a hypothetical generator at this point, maybe if you did some maths, you could move the generator up and down and see how much is going up and down on that line that you're worried about. So in this case, and I'm going to pull out my pointer here so I don't stand in front, 21% of it's going that way. Nothing's going on this lightning line because that one's the one that failed. Maybe 20%'s going that way, 20%'s going that way, 20%'s going that way, and maybe a little bit's going all the way the long way around. So that's this idea of sensitivity. You care about the one on the line that's maybe getting damaged. So we care about this 21% number. That's a sensitivity. And 79% is going through the other spider web paths in the network. If you had a hypothetical facility here, we don't have facilities here, this is all hypothetical scenarios, then maybe you could calculate how much power is going this way, how much power is going this way, how much power is going up and around and this way, and in this case maybe it's 10%. The reason I included facility on this side is that a facility there would probably have power going the reverse direction. It would have a negative sensitivity. For every megawatt you turn this facility on, it's solving the problem. So that's the idea of sensitivities, which is core to any constraint equation, generally speaking. Now, how do we get from limits to sensitivity? And it kind of changes drastically whether or not you're talking about a thermal limit, which we have a relatively solid understanding of, and a non-thermal limit, which is a bit harder, a bit non-linear, a bit more difficult to turn into a constraint equation. So for thermal limits, say for example, keep this line under 90 degrees. It's a pretty standard thing in electrical network world. We need to convert temperature into something controllable, i.e. dispatch of a generator. We might start with the temperature, and we might be able to convert that to a current limit by considering how much heat losses there are on the line, what the ambient temperature is of the line, and that kind of thing. So you can convert temperature into a current limit through that kind of law, the laws of physics, basically. You might be able to then convert that into an apparent power level because you know what the voltage is going to be. Not exactly. You might apply some kind of fat margin, but you know it's going to be nominally this much voltage, so then you can get apparent power. And you can convert apparent power into a real power, the thing that we have more control over, by considering what is the worst case power factor you might be thinking about. And we do that. And the final step is sensitivity that I just talked about. So now you have a real power limit on the network, you can convert it into generator limits, and boom, you have all that you need to make a constraint equation. For a non-thermal limit, excuse me, my mouth is very dry. The limit might be something like keep the voltage compliant, keep the voltage above 0.9 per unit after a fault or something like that. We have to convert that into something controllable to dispatch of generators, which is difficult. So the way we do it, and this isn't the only way to create a constraint equation from a non-thermal limit, is to identify lots of scenarios that are on the limit and lots of scenarios that are not on the limit, and try and draw a line between what things are when you'll be safe, which dispatch conditions will be safe and which dispatch conditions won't be safe. And you draw that kind of linear regression, you can get apparent power and then use sensitivities to get to real power. But the idea is pretty much any limit that you have, doesn't matter what it was originally presented as, you can do some trickery and some math and eventually end up with this dispatch this and this less than a certain number. You get a constraint equation. That's what a constraint equation is. All right. The other concept that causes quite a lot of confusion in constraint equation land is particularly relevant to network access quantity models is this idea of a pre-contingent or a post-contingent constraint. So here is a lovely contrived example where we have two perfectly parallel lines of 100 megawatt limit that we converted using some temperature to current to shenanigans. And we have two generators here, A and B on one side, generator C here, and the load that it's being supplied. It's a very simple network. The idea of the constraint equation that you might look at initially is that we have to protect the top line from overloading. So we can make a constraint equation for that. We can say that roughly, because this is a very simple network and it's obvious, half of this is going the top way and half of this is going the bottom way. So half of A and half of B needs to be less than 100. My first constraint equation, trademark, copyright, great. That's a pre-contingent constraint, that's what we call. Or a nil contingency constraint I think we have in AEMO's dispatch engine. The second case is at any point in time a thing could go wrong. Lightning could strike. I had some nice images to remind me. We could have a bushfire that has smoke and trips a line. We could have somebody with a big truck of petrol drive into a pole and start some serious damage. Or like I think a couple of months ago we had a freak weather event that pushed some poles over somewhere in the east. So anything could happen at any point in time. And the second that it does happen, all the power from these facilities, which aren't suddenly disappearing, we've got physics that says energy is not created or destroyed, it's there, is now being pushed through the last line. So what that actually means is you have to think about it like this line doesn't exist, and A and B need to be less than 100. That's always worse than the top one. There's very few cases that we actually make these constraints because there's always one of these that's worse. So that's the idea of pre-contingent and post-contingent constraint. It can be quite confusing for somebody designing a facility because they go, well, I know the rating of this line, so I must be able to do this. But we have to consider what can go wrong and every combination of things that can go wrong. All right, so if you have that knowledge of pre-contingent constraints and sensitivities and limits, you can make a constraint equation. The network access quantities, as I started off by saying, is just merging those two concepts together and dealing with a little bit of the nuance. So the big question that we need to ask, in addition to our first big question from capacity mechanisms, is will there be network restrictions during our time of need? That's the thing that we didn't know. So before the network access quantity model was developed in Western Australia, we had what's called unconstrained access to the network. So everybody who connected could in theory do absolutely anything they want in terms of dispatch and it shouldn't be able to damage the network. But that's an overly conservative way of designing the network, and the trend is as the network gets bigger that we don't do that anymore. We allow constraint equations to protect the network and we allow more facilities to connect to the same level of network. But we now have to answer this question: will there be network restrictions? The fundamental idea is that a network access quantity is what the constrained output of a facility is in 95% of the scenarios that you're testing. And we're going to unpack that statement, but that's the core idea. We have this idea of constraint equations and what we can and are allowed to do. We create a lot of dispatch scenarios, we meet those constraints, and we figure out in 95% of those scenarios, what did you do? That's what we can rely on you for at the peak. And to unpack that, I've got 4 examples and I have some lovely pretend facilities that are definitely not real. The first concept that I'm going to introduce is the idea of network configuration. When you have a constraint equation, and we talked about those sensitivities and how much flow is going on, every little assumption you make about exactly what the network looks like can change those constraint equations and hence change the outcome of your network access quantity model. So the first concept is we need to agree on a single network configuration that will make this work. Or we call it a most likely network configuration at peak. And maybe you can have a couple and average them out or something like that. But the idea is you need to agree on network state somehow. There's lots of different ways that a network configuration can change your constraint equations and can change your NAQ outcomes. For example, if you agree that a certain element is out of service at peak, or you agree that a certain element is in service at peak, that will change every sensitivity in every equation nearby, which would mean that whether or not an equation binds changes and you get different NAQ. If you decide that there's a different temperature at your peak event, is it a 41 degree day? Is it a 45 degree day? Is it 45 in the north and 41 in the south, or any combination thereof? Every time you change the ambient temperature, you change the dynamic temperature limits of all the lines in the constraint equations. So whatever you do here is going to change your answers. The third thing that can have drastic impact is load. One thing is your total load, how much load is there overall and how much facilities are on. That's going to change how much competition there is for any given limit. So if all the numbers are higher in every constraint equation is going to bind more often. Similarly, if you decide that during a peak event there's more load in the north because there's more aircons in the north, or this industrial facility is off or on, you're also changing how much flow there is to that facility and how much is left over for all the facilities to compete. So you have to be very clear about what loads are in this most likely scenario. And another one that makes quite a lot of work for people, for me, attempting to apply this mechanism is the idea of schemes in the network. Special protection schemes, also known as network reinforcement schemes, also known as remedial action schemes, schemes in general. And what I mean is any system that automatically reacts. So the reason we have a constraint equation to protect against something in case something goes wrong is because we can't change the output of a generator quickly. We've got maybe a 5, 10, 15 minute lag before we give a new set point, by which point the equipment's already melted and broken or whatever else. We've started a bushfire. Schemes let us bypass that. So we might have a scheme that says, if this line is overloaded, straight away trip that generator because I know something's gone very, very wrong. In that case, you don't have to have that facility in your constraint equation anymore. So that facility becomes unconstrained and you get more capacity in your network. So what you decide is going on with the schemes, whether or not a scheme is in or out, whether or not there's a new scheme for a new facility, can also drastically change all of your results for your network access quantities. So we definitely need an agreement on what the network configuration looks like. Finally, obviously, the network's not the same. So over time, we're going to build new bits of network. So whether or not a particular piece of network upgrade is in or delayed or hasn't been designed yet also drastically changes all of our results. Second concept, and I'm going to have more pictures from now on because it's very hard to do the first one with more pictures, is an idea of an objective function. So I said we're solving for all our dispatch scenarios. What can you do in 95% of them? How do you solve one dispatch scenario? That's where this comes in. So the idea that we've implemented in network access quantities is this idea that we must minimize the change in dispatch. That's a different objective function to what normally happens in normal power system operation, where the objective function is always what is the cheapest way to do it. In this, we just want to know that we can do it, because that's the number one question. Can we meet the peak? Not is it the cheapest way to meet the peak? And if you unpack that into more words, in a single scenario, if any particular constraint equation is being breached, if we're predicting that something's going to be melted, the way to fix it is to reduce the facility with the biggest sensitivity, because that'll have the most impact per megawatt and the least amount of movement on the system. It also means you'll get the biggest number of megawatts for the same bit of network possible. So that's the objective function. To illustrate that concept, here is an arbitrary 40 megawatt bit of network. And here are three facilities that I have called Windy Valley, Sunny Hill and Smoky Port, coal plant and solar hybrid and wind farm. Three facilities, all 100 megawatts, and that's 100 megawatts after we've applied all this stuff about relevant levels. So nice round numbers to do some nice easy maths. If it's got 10% sensitivity, 10 megawatts are flowing on that line. If it's got 20% sensitivity, 20 megawatts are going on that line, and so on. And if you add all those numbers together, you'll see that there's 45 megawatts trying to go through something that's only 40 megawatts. So if we fed this into our linear model, that thing would be breached, and we'd listen to our objective function, minimize the change in dispatch. And what that means is we're going to reduce the one with the biggest sensitivity, the thing that's probably closest and on the wrong side of the thing that might be getting damaged. In this case, it means reduce this thing. And if you're doing maths at home, we need to get 5 megawatts out, so we need to reduce it by about 25%. Cool? So that's the objective function. And this works together with the next two concepts because it's all being solved in a mishmash computer. You can't do them individually. Concept number 3 is an idea of priority. if we don't have a concept of priority is the number one question. What it means is that a new facility can come along, connect 1 centimetre closer to the centre of load than an old facility, and steal all their capacity credits in a congested network, which is obviously bad. It means somebody has come along, invested in our network, built a generator, and relied on a certain amount of revenue from our capacity mechanism, and then I'm going to get it because somebody came along and stole it. So priority is a really important issue for that reason. We need to make sure that existing facilities that helped us when we needed them are protected and get that revenue that their facility exists based on. However, if we assign credits to people, as we have previously done, completely ignorant of the fact that the network is changing, then we might not predict that we have enough capacity credits. If we don't ever reduce somebody's capacity credits, then we might think we're okay and in real time be 100 megawatts short and have to load shed the Prime Minister's house, which would not be good. So these two working together, we have to protect existing providers, but not at the expense of reality, as much as possible. That's the two key priorities here. I've noted what about upgrades. If you had an existing facility and they wanted to double their size, go from 10 to 20 megawatts, it's kind of thought that maybe I should get priority because I'm existing, I helped you out. But if we did that, it would mean that everybody existing would have a massive leg up of everybody who's not existing. So we'd be kind of shunting everybody new from entering the market. So upgrades are not here. They're not an existing provider. Upgrades are new people. The third thing we want to do is reward network augmentation. Historically speaking, before the NAQ, everybody who wanted to connect had to augment the network to connect. But obviously, as I said, that's not necessarily efficient and can be quite costly for new participants. But we still want to reward it if they can, and if it's the only solution, then we have to have, somebody's going to have to augment the network. The person augmenting the network should get priority over somebody who doesn't. Makes perfect sense. And if we do that, we have this concept of network access funding facility. They're going to get capacity credits before somebody who doesn't augment the network. But not at the expense of existing providers. Just because you're building a new power line over here doesn't mean you get to steal capacity from Joe over there. And the fourth category of priorities is an idea of certainty. So this isn't necessarily essential to the network access quantity model, but we sort everybody who's left based on this idea of how certain they are. If they are committed, if they have a network access contract, if they've already started building, we're much more likely to get their capacity when we need it than somebody who has an idea for a facility but hasn't necessarily got any of the planning approval. Because what happens if some kind of roadblock happens? What happens if they can't buy the land because there's some lien on it or something like that? So a facility with certainty, generally a facility who's committed, is preferred to a facility who isn't, and they get a leg up over people who isn't. But they don't get a leg up of anybody who's funding the network, and they don't get a leg up over anybody who is existing, because otherwise all these principles we just talked about break down and we don't have a mechanism that really does what we want it to do. To illustrate this, same 40 megawatt limit, same Sunny Hill and Smoky Port, but now let's just pretend that Windy Valley is a new facility. It's coming along, it didn't exist before. In this scenario, we know that there's 35 megawatts here coming, so there's 5 megawatts left, but to fully allocate Windy Valley in this particular scenario, we need 10. So we have to restrict it by 5 megawatts because we're protecting these existing providers, and even though we'd like to reduce Sunny Hill because of its nice, juicy, big 20% sensitivity, we are going to reduce Windy Valley instead. That's how we protect existing providers, and it's reduced by 50% or so. The fourth concept of the network access quantity model that works together, I will do questions in the middle if you like.
How long is it new for?
How long is it new?
Yep. Is it new forever?
Oh no, it's new in the cycle that it enters. Okay. So after it's entered, the network shouldn't, in theory, get much worse over time, so it's now considered existing the same as everybody, but only up to the level that it got credits. So yeah, there's a bit of nuance there that I'm not going into detail, but the idea is you have priority for your first 5 megawatts. Everything else after that is slightly less priority. All right, fourth concept, and the last one that works together to make a network access quantity model that we've got, is an idea of probability. So I started with, we are looking at 95% of scenarios. And that idea is quite important for trying to edge out the edge cases where, yeah, if every single generator in that part of the region is on, you've probably got congestion. But if you've got 4 gigawatts of generation, the chances of that actually happening in your peak event, the chance that every single one of them is not the one on outage, the chance that all of them have wind is not very likely. So this idea of probability is quite important for having a realistic view of how much capacity credits you have during your time of need. So imagine that we have just enough capacity credits to meet our load. On that load day, assuming our load forecast is good, everybody's on, which means we don't necessarily need to worry about a cost per unit of energy because all the facilities are on anyway in this kind of mechanism. So with that in mind, every facility is required, and so every facility is equally weighted in our randomly generated dispatch scenarios. There's no reason to turn the diesel generators that are expensive on less, because during our peak event, we've tried to get just enough capacity credits, they're on. So it doesn't matter that they're diesel or not, they're going to be on. To illustrate that, here's the example from the previous slide. We have Windy Valley is new. Our randomly generated dispatch profile has all of them at max, and that means that we have to reduce Windy Valley by 50%. What if, in another randomly generated dispatch scenario, Solanke Port wasn't on? Instead, another generator somewhere else in the network that's not relevant to this piece of equipment was on, so there was no problem. In this particular problem, Windy Valley is not limited. That's 2 scenarios. Then we're going to do it again and again and again and again and again and again, tens of thousands, hundreds of thousands of time using a nice computer that I wouldn't be able to do manually, and we can come up with an answer. 95% of all these scenarios, they were reduced by 10%. So let's give them 90% of their relevant level in capacity credits. Make sense? So that's the idea of probability. That works together with the other 4 concepts to create a network access quantity model. We need constraint equations. We need all these things to work together. Otherwise, it doesn't work. Cool. So that's network access quantity models. And now, as I said, we've run this for 2 years and also another 2 years before that in draft. We're not publishing any results to see how it works and to eventually assess and allocate capacity credits to our network here in the Swiss. In the 2022 cycle, the first time that we formally applied this, we took everybody's capacity credits from the previous year and we put them into our lovely complex machine that has limits and constraints and probability and non-thermal stuff and sensitivities and priorities and all that kind of stuff. We shoved them in our model and out came that their capacity credits were equal to their NAQ. No reductions, tick, 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 everybody's happy, job done, walk away. Which in the immortal words of my colleague Stefan in the reserve capacity team, who spent many late nights with me trying to get this working, oh my goodness, this is the most complicated unity function ever devised by mankind, which is true on the surface, if it didn't do anything. But yes, it was on the surface. Behind the scenes, a lot of work between me and my colleagues in Western Power to figure out how do you interpret this rule? What does the network actually look like? Have we got the right limits here? And in fact, a couple of network augmentations that were planned for a few years in advance were brought up so that the NAQ model would solve to get this outcome because the network was unconstrained and it should have been unconstrained. So that's the first cycle. So even though it looked like nothing happened, a lot of work went in behind the scenes. The second cycle, which is the first time that we actually reduced somebody's output, is more interesting because as soon as somebody's financial revenues are impacted, that's when all the questions come in, that's when everybody starts to get concerned. So I have to do this without being specific about locations, but that's a load center somewhere in the world, and here are 2 strong connections to the grid, to the reference node. We have a weak path over here, 2 strong paths over here, a bunch of network that looks like this. We have some generators in this point and some generators here. And when we ran our modelling and tested all the different things that could go wrong, strike some lightning here and feel very powerful like a god, our modelling was telling us that if you break this one, then that one's going to get overloaded. They're parallel and it makes sense. Anything that was trying to get to that way is now squishing through the same pipe that way, and it might be overloaded. And what we did when we ran the NAQ model through all these priorities and all these steps, it told us that we would need to reduce these facilities by 20% in order to not breach that limit 95% of the time. So those facilities got a NAQ reduction. And as I said, being the first time that this mechanism has impacted the revenue of somebody in the market, it's quite a stir. And we get lots of questions. So a couple of questions that have come up. I meant to bring that up in 2 dots, but that's okay. First question, if a facility is next to a big industrial load. I'm a 10 megawatt facility and here's a 100 megawatt load. Surely all of my power goes to that load. How can I possibly cause congestion? Why should I get a NAQ reduction? Which seems in isolation like a reasonable question, especially if you're not worried about all these complex ideas that we've been talking about. The core answer to that question is this idea of a reference node. So every constraint equation, and this is in the rules, but it's also quite common practice, every constraint equation, every limit, the facility sensitivity and its contribution to the problem is with respect to its path from where it is to the reference node, which is Southern Terminal in our case. So what we're saying is this facility, even though it's right next to a big load, in effect its impact on the network, its sensitivity, the way it contributes to constraint equations, doesn't know about that load. It only knows that it's going to Southern Terminal. And the load itself has a coefficient with respect to Southern Terminal. If we break that down another step further, what the idea of a reference node is saying is that nobody has priority to any given load or any given generator. You're all going to Southern Terminal, and then we let the computer say who is the most efficient contribution to go to Southern Terminal. More importantly, if we didn't do this and we said, well, yeah, that facility can't be constrained, we reran the model just to see what would happen. And what happens is the next closest facility, which has maybe a smaller coefficient, to fix the problem, you need to constrain them more. So instead of constraining 20% of this facility, maybe 4 megawatts off the market, you have to constrain 50% of this facility and you lose 50 megawatts from the market. So the reason why the model was saying we need to reduce them is because that's the way to get the most capacity in the system. It's the correct outcome, but it doesn't seem intuitive when you're an individual looking at my little corner of the network. Second question, one of those facilities that got reduced is a demand-side program. So demand-side programs are treated just like any other generator in this mechanism. They are effectively a generator of the size of how much the load can reduce at that point. What that means in other terms is that if you reduce the load, you might increase the problem. It doesn't necessarily always guarantee that reducing a load reduces the problem. And we test that. We can get a load, we can reduce the number and see what happens to the line that we're worried about. And if it goes up, it causes a problem by existing. So it's very reasonable to constrain it as a demand-side program. And in fact, the same answer, because they're at the same location. If we didn't allow DSPs to be reduced, we sacrifice more capacity for the network, which isn't the correct outcome, even though it feels a bit wrong to not let a load go down. You might say, Lucas, a load can go down whenever they want. You can't control the dispatcher loads. That's true. I can only control the fact that our control room won't make them go down. But in real life, if they went down, they'd cause congestion. Someone would get constrained as a result by the engine. But that's okay. We've decided on what the most likely network configuration is, part of which is the loads. We've decided that it's very likely that this load is on in our peak scenario, so it's quite reasonable to make the judgment call that we shouldn't call the DSP, even though there might just not be there in real life. All right, that's the lessons that we've learned from running it for a couple of cycles. The last little bit of my presentation is about some issues that we're working on that we can see with this mechanism, especially as it unfolds over multiple years and things get more and more complex. The first issue is that I've had an enormous amount of queries from market participants trying to estimate this. As I said, part of the reason to have a capacity mechanism at all is that you need certainty in your revenue so you can get funding to build your facility in the first place. So if somebody can't estimate what their NAQ is going to be, or more importantly, prove it to the bank, how do they get that funding and how do we get any facilities? So being able to estimate your NAQ is an important issue and not necessarily as easy as it seems. In theory, every input you need to do what we've talked about is publicly available. You can sign a non-disclosure agreement and get a network model. You can get all the ratings. You can get that's published on AMO's website and so on. And you can create your own linear solver that has an objective function, and you can do this maths, but nobody's done it in detail yet. It's quite difficult. And in practice, even if people have tried to do it, it's been quite difficult. So whilst the market is getting more familiar with this idea of network access quantity models, and people with constraint equation experience are coming from other parts of the world to WA to boost our skill set, what we're working on is a way to try and give some level of information so that market participants can do that without a consultant. More importantly, if we expect people to do this work, which is quite complicated, and they're a small participant, it might not be financially justifiable to get a consultant to buy massive amounts of engineering time to try and estimate what your NAQ would be for a 10 megawatt facility. It doesn't make much sense. So what we're working on is a publication of likely NAQs at a location if you ignore everybody else. It's a bit of information, lets you get a bit of a judgment call about whether or not your facility can go there, and hopefully is enough for small participants to overcome this problem, whilst consultants are getting more familiar and hopefully cheaper in being able to do this for market participants. The second part of that, and I say this with lots of caveats because it's a lot of work for me, is a self-service tool. So we have a model. In theory, I should be able to put it on a computer and let you change the inputs. Have exactly the same NAQ model from last year, add a 100 megawatt facility here, tell me some answers. There's no reason we can't automate that, with the exception of it's a massive amount of work that AEMO is not necessarily funded for. So yeah, the issue here is that trying to get those numbers out to the people who need them. Second issue is a concept I'm calling uncapped protection. So there is an idea in the rules, and it's quite common in constraint equations in general, to say small coefficients. The reality is my 100 megawatt facility might move something by 0.5 megawatts over there, but my contribution is so small that it's going to skew the outcomes. It's going to turn me off for almost no reason. So there is something in the rules, and we've implemented, that says capacity sensitivity factors and constraint equations below something. Too small, don't worry about them. But in our mesh network in the Swiss, there's still a lot that fall above that threshold. So, and recall that discussion about how sensitivities work. We have quite a big spider web. It can mean that if a network element has sensitivities from everywhere and it's highly loaded, which is the case for some of our network elements, that as you try and add a new facility in the middle of nowhere with a 3% coefficient that might be above the threshold, you might need to constrain it 100% in order to get a tiny bit of benefit. But you're only doing that because it would be much more efficient to do the existing generator that's right next to it by 2 megawatts. What is a good ratio there? Should you allow constraint of an old facility for 1 or 2 megawatts to save thousands of megawatts over here? There's a question there which isn't necessarily solved as to what is an appropriate ratio. In other words, the other idea here is that we separate these two mechanisms altogether. We have a capacity mechanism that works purely based on what can the network do, and little uplift payments that if it moves around, you get uplift payments. But the core problem is, if we have the rules as they are right now, and we have a network element that's loaded, the only thing we can do is augment the network. There's not really anything that can be done in terms of what's a reasonable trade-off. The third issue I want to talk about is that this whole process is quite sensitive to how much generators you have. You recall one of the examples we talked about, randomly one of the facilities is 0. Expand that idea a bit more. If we have 4,000 megawatts of facilities and the load goes up and we have a new gigawatt of facilities entering the market, our randomly generated dispatch scenarios, if we have heaps of excess generation, everybody gets turned on less, and every constraint equation binds less, and everybody gets more NAQ. So as you get more facilities, every facility's NAQ gets bigger. So we get this exponential effect when we have an excess in capacity, and the same in reverse. If we have not enough facilities, that means almost every facility is on in every scenario, which means every constraint equation binds more often, which means everybody gets exponentially less credits. So what exactly our total generation is, how many people are applying, has a massive impact on everybody's NAQs, which doesn't feel right. It doesn't feel as an individual participant that the fact that somebody else didn't commit their 300 megawatt facility should impact my NAQ. But it does in this mechanism. So that's the core problem. And the fourth issue, which is related to my friends here in the audience from Western Power, is this idea of the network configuration that we talked about earlier. So what the network configuration is according, in a peak scenario, according to the network service provider, according to what has historically been designed, according to whatever reason, might be different to the set of network configurations that you have in your NAQ model, because you've agreed that this is the most likely NAQ scenario, even though it's the most likely peak scenario, it might only apply once every 10 years. So why should we design the network for that? There's a trade-off there between what's economical, what's logical. And the core problem is that there is a difference. right? So if there is a difference and a network service provider gets a query from market participant and says, yep, this part of the network looks great for you, you shouldn't get constrained at all, and then they go to the NAQ mechanism and the NAQ mechanism says, well, in our 1 in 10 year event, you probably will get constrained. Both of those things are true, but incredibly unhelpful for the market participant. They might have committed a whole bunch of stuff on the basis that the network's probably okay 90% of the time, but they were relying on this NAQ funding, which now they're not going to get. So there's a whole bunch of work here about how we not only close that gap, but come up with an idea that's, we're still trying to respect the realness of the market, the realness of the networks, the realness of where all the money flows. So we don't want to get rid of the idea that the network service provider might design the network to something that's different than the NAQ, but we do need to bridge that gap and give more certainty to the people that are investing. So that's the 4 issues, and I had 4 concepts, and I had a couple of background knowledge. That's pretty much it for me. Any questions? Silence. Maybe I did such a good job. Here you go.
Hi, Esam from Curtin University. Thank you so much for the nice presentation. Actually, the one that you mentioned as one of the problems about the total generation, that was the main question I had from when you were explaining about the previous topics. So eventually, as the outcome of the NAQ, then you want to use it. So I wonder how you're going to apply it. Like, is it like telling those generators to reduce the capacity? Is this the outcome of the NAQ? Because you are limiting the generation to improve NAQ. If I'm not wrong, this is the understanding that I have now. In order to improve the NAQ, you have to reduce some generations. You have to put some limit on the generators.
I think you might be talking more about this one, about uncapped protection. Because the issue of too much generation is the fact that the NAQ is sensitive to having lots of people. This one is saying that it might be more efficient, right? So your question's on this one, right?
This one and the previous one generally. So I'm trying to get the practice of this one, how practical will be as the recommendations eventually. So in order to improve NAQ, how are you going to apply this? You're going to ask the generators to limit the capacity, to reduce the capacity?
Well, right now, as it currently is, and for good reason because of the priorities that I talked about, the idea is that the existing providers are protected at all costs. And what it actually means is that somebody else applies in a distant part of the network, unless they fund a network augmentation or unless something changes in the network voluntarily, they get nothing. But that's the problem. We need a lot of energy for our energy transition, right?
Conflicting.
So right now we're erring on the side of definitely protect because it's important, but we need a way to imagine hypothetical alternatives that a new facility comes along, augmenting the network to fix the problem, $1 million piece of kit, more, I don't know, I'm completely alien on what the network costs, except that it costs a lot. What if instead they bought some capacity credits from a guy, from a person, that has capacity credits in a bit that's limiting to them? If we allow that somehow through some kind of mechanism, then that would sort itself out over time. Or maybe the other idea that we had is maybe hypothetically we let facilities be reduced if it's more efficient for the network, but we keep paying them, the market keeps paying them for 10 years or some kind of fixed period based on what they first got. There's a lot of ways to solve that problem, but it's not an easy answer, right? Each one of those has swings and roundabouts. We don't really want to be paying for generation that we can't use. We don't really want to make a complex market of trading capacity credits because then whoever got here first has massive money advantage. It'll be like the dot-com boom again. So, it's lots of potential solutions, but yeah, it's not an easy answer.
Thanks, Lucas. Dean Frost from Western Power. Another hypothetical. Into the future, there may well be another network operator with a significant amount of generation and load, and it would necessitate perhaps considering establishing sub-regions. There might be a trigger for consideration. Assuming that the tools are fit for purpose, conceptually, how might you reevaluate the NAQ process?
Well, I think even if you've got multiple providers, and this is the case for AIM over East, you still have a network model of the whole thing. So you would still, even though it might, there might be a bit of discussion between the network service providers, you would still come up with an agreed network configuration, even if it's stitching multiple future worlds together.
The reference node though?
Yeah, I mean, if the network gets big enough that it warrants having multiple reference nodes in every constraint equation, then yeah, it could very well mean that we could do that. And all that means is that when we build our constraint equations, if the region that is under consideration is over here, you use that reference node. If the region is over here, use that reference node. And they can still work together because the reference node itself isn't determining the equation. It just changes how big or small the coefficients are and how much you ignore the flow between regions. So I think, yeah, you would just make the constraint equations as you might do, as they already do in the east, but they have multiple reference nodes. It's with respect to the one that's most relevant and close to you.
Are you suggesting, Lucas, that the NAQs that were used before the hypothetical scenario would remain much the same?
Yeah, so a transition's going to be the big deal, because if you suddenly change the method and you have different constraint equations, then there could be a drop up or down for any given facility in any given year. I would think and hope that we do what we did in the first cycle. There was this idea that everybody who existed in the network before this mechanism coming in had some kind of priority, some kind of right to a consistent revenue, and they were given some kind of top up. And I would think that if we decided to make a big change, like multiple reference nodes or changing the temperature calculations or what have you, that we'd have a similar mechanism where whatever you had in the year before the change, you get some kind of right, some kind of top up to get you there, even if it doesn't change your actual calculation, just changes your financial outcomes a bit.
Thanks, Lucas.
Hi, this is Kai from Electrical University. Currently we are working on electric vehicle system, and we also have target for net zero carbon emission 2050. So there's a big and giant demand for electric vehicle system that we may need to manage it. How can you manage with your NAQ current system, and how do you have any plan about the future?
Yeah, so IES electric vehicles have two ideas associated with them. One being that it's a lot of load, and one being that it's potentially a generator. So we have a whole bunch of stuff I didn't really talk about here in terms of aggregators, which applies to the second concept. Maybe I'll talk about that one first. The idea is an aggregator can participate in the market. There's no reason it could. In an ideal world, we know how much DPV how many EVs there are, how much of every aggregated resource there is at every node, and we treat it just like any other generator. You might have a person who aggregates them and says that I commit to ensuring this much controllable capacity of EVs and what have you, and then they can participate in the rest of the mechanism as it works. They're just a generator that gets chucked into every constraint equation. So there's no inherent problem with that. The problem that we have with aggregations generally is that they don't know 2.5 years in advance, and they can't guarantee absolutely where every one of their facilities is going to be. That's difficult. That's a hard question to answer. There's some trial rules going in around this space. An idea being that there are lots of parts of the network that are not constrained. So we should allow aggregators to play in that playground for free. There's no problem. So the idea is if you're small enough and you're playing in these areas that are relatively uncongested, go for broke. You don't even have to be in the model. You just get the capacity credits and everything's fine. If you get to a certain size or in a certain location, then you have to participate properly. You have to oversubscribe to guarantee a certain amount and be like every other generator. The first issue of the electric vehicles just being a massive load spike, that comes down to where you assume the loads are in the peak event. So you're hoping that mechanisms outside of this are encouraging people to not have their electric vehicle charging during the peak. And if they are, then they're in the model. They're underlying load that has to be supplied by some other generator. They might cause constraints, they might not cause constraints. But the idea is this model is more about assigning numbers to the generators. What a load gets done is not really considered in the model. You don't need to worry about it. You've got, this is what the load is going to be in the peak scenario, and generators, this is what you're likely to do. That's what the congestion is likely to be.
Thank you.
Cool.
The concept of NAQ is not something new, so it has been applied to other grids. The learnings that we have here, are they aligned with other systems?
I wish I could tell, but I'm not that familiar with what's been done. unfortunately. I have to do more research, but yeah.
Okay, I have one question. So with the bigger loads getting connected to our network, obviously the configuration that NSPs would consider might change. Assuming that we've got 300 megawatt lump load connecting somewhere in the network, how's that going to impact the NAQ for the existing facilities? Because the contribution might change, the pattern of flow is changing, lots of changes in that.
Yeah, I would think that generally speaking, if your 300 megawatt or your big scale load's going to connect in a in a location of the network suitable for it, probably on the backbone, and that would probably mean that other generators are going to only benefit from such a big load. There's more load for them to supply. It's only if we put block loads in parts of the network where they have a negative coefficient, there's not too many of those, but in pockets of the network where a load going down is a bad thing, which would cause a problem. But that's not going to happen for a 300 megawatt load, because to get that 300 megawatt of power, you have to do something to connect it, or it's got to go on a strong part of the network. The other problem, which I guess you didn't touch on, but this idea of there's so much uncertainty in what the load profile could look like, especially if you've got lots of potential customers in all different locations. We were talking about it a bit before the presentation. I think the only solution to that is we've got one model here that deals with one network configuration and hundreds of thousands of generation dispatch profiles. But at some point, it's going to be too hard to assign one load profile or one network configuration. And I think the solution to that is to start thinking about multiple network profiles. So it might take us a day to do one of the scenarios. There's no real reason, given enough resource or time or computing power or the advent of quantum computing, that we can't do several scenarios and maybe average them or give them a probability weighting. So if there's a 10% charge of a 10% chance of a massive load, then you get everybody's NAQs for both scenarios, and you go 10% of this and 90% of this per rudder or something like that. So I think it can be handled, yeah.
Carrying on from that is where you talked a little bit about getting consensus about what that load profile of the network configuration is. Who's involved in the consultation to come up? Who's involved in that consensus decision? Is it industry widely? Is it within AEMO?
Yeah. So I mean, the way it works here is that. In our mechanism and our rules as they are, is that everything except for the total load number is known by the network service provider, Western Power. So they're the ones who know what projects are committed, uncommitted. They're the ones who know which loads have a contract to reply. They can make judgments about what the most likely scenario is. So in actuality here, in our mechanism, we have almost no input on what that scenario might be. Whether or not that changes over time, if this has a big impact and a big interest in the market, and lots of people, their entire livelihoods depend on exactly what that load scenario looks like, then I reckon the consultation for that and the opinions for that would grow. There's probably going to be rules added that we have some kind of consultation period on that. But right now, the network service provider has all that information and has been doing that judgment call for a long time to build our network for a long time. So it's entirely with them.
So that's not the ISU load forecast, that's the one for power.
Yes. So okay. So the AEMO decide what the peak load is as part of the ESU, Electrical Statement of Opportunities. I don't know how familiar you are with that, but generally our 10-year plan for what generation should be if network doesn't change. And the network service provider has their own planning reports for different scenarios. The limit advice that feeds into this per the rules is AEMO decides that peak number, because we have done forecast modelling of that kind, and Western Power does which substation has how much of that load based on their knowledge of all the connections and things like that. And even that first one, the total load, it's still very much a group effort. It's a complex problem, and everyone chips in ideas and probabilities and things about that.
So in terms of scenarios you're running, what are the variables within that you're considering in your probabilistic distribution? Is that
Only generation dispatch.
It's only generation dispatch. So your assumed peak load is fixed, and that's based off of
The ISU forecast, the 10% POE in 2 years' time,
2 years' time. So it's
and we run it in a 2-year cycle.
The year they first get their credits, essentially.
So we rerun the NAQ every year, and an existing facility, if the load goes down or up and that benefits them or disadvantages them, their credits can go down and up. So there's no guarantee of a fixed capacity credits. But as I was saying, that's a bit of a problem. If you're going to you need to prove to a bank that you've got a certain amount of revenue through this mechanism, then having uncertainty around what your future NAQ's going to be is a problem. So maybe there's an opportunity there to provide some kind of guarantee mechanism. But the idea is no, if we respect, the number one priority is we respect the reality of the network. If the load forecast has gone down for some reason, and that is a problem for you, then it's a problem for you and you have less NAQ.
And it sounds like it's a once and done process, right? So if I'm a participant within your facility that's considering investing, I just find out my NAQ after the fact.
Yeah, there's a bit of nuance there in the rules. The key point is that you can apply to be part of this mechanism, but also say that I will only proceed if I get at least this much, because I need this much for my bank approval or whatever. And if you don't get that much, the model will take you out of the picture and put the next person in the priority back in until we solve it.
So how do I, as a participant, understand the value if I also pay for network obligations, or I'm willing to? So is it I have to wait a year to reassess?
Yeah. So
Fully reassess under that.
Yeah, the idea of network access funding, obviously we can't run a million different network scenarios if each participant wants to augment different bits of the network. So what it has is only the concept of most likely. So if you have applied as a network access funding facility and you have a reasonable design for what network you might augment through your discussions with the network service provider, then we assess everybody existing against the existing network, and we do a second stage where we assess everybody existing plus the people who are augmenting the network with the augmented network and proceed down from there. So two states of the network. So there is provision for that, and that's how it works, yeah.
I don't think we've ever actually done it though.
We have not done it, no. We've actually, had lots of people have on their form that I'm network access funding facility, but there's a bit of miscommunication about what that means. Network access funding facility, as in I'm paying to connect to the grid, is different to, because that's not a network access funding facility, that's just connecting to the grid, is different to somebody who's willing to augment a network somewhere else, because that's the thing that's causing them a NAQ downgrade. And if you are willing to make that capital investment, perhaps the capacity credit differential is big enough for you to make some kind of contribution to that network, then yeah, you compete with existing facilities and anybody else who's funded a network augmentation for a model that has all the network augmentations. So just two steps.
I think in practice it tends to be existing customers that are connected who have then had a reduction in NAQ.
Who want to augment again?
Investigating the possibility of an augmentation that would see that
Because it's
better
actually
result than actually. Is that sometimes that 1 year delay that you talked about is typically what you see?
I might also throw into that, I didn't go into it here, obviously there's a whole lot more levels of priority. In fact, we have like 40 levels of priority or something. But there is a concept in here about if you've ever had capacity, then you have priority over somebody who has never had that level of capacity. So you get assessed up to your highest previous capacity credits before it's opened up to every existing provider having what could they possibly do. So there's that level of existing facilities is actually broken down into lots and lots of steps still, but no point when we're just talking conceptually about, the core point is we protect existing facilities, but yes, if your network went down and then the network was augmented or the load changed and goes up again, you have first dibs on that capacity from somebody who didn't.
I was reading about this for the first time, and I'm just kind of thinking, if the load's growing okay and the network's highly constrained, and this mechanism is kind of incentivizing generators to invest in capacity, but if those capacity credits needed to meet the load are preserved, and So in such a way that these new generators just can't have enough capacity credits allocated to them because they've been allocated to other people, and the network's very constrained, and therefore for them to actually be able to enter the market, they've got to reinforce to build a network. Isn't that a barrier in the sense that, so it's sort of counterproductive? You're not going to get the capacity in a year. You won't buy this mechanism because there's barriers of network in the way that would need to be overcome to incentivise these. So from an industry point of view, what's the solution to that?
Look, I don't think it's necessarily incorrect to expect a participant to fund network augmentations. They were doing that before. The idea was originally, hey, we've got all this network, it should be able to do more. Why can't I connect and just be happy to be constrained 10% of the time? That's what we're allowing. That's the fundamental reason for going through all this effort. But if there's no capacity left in that peak scenario, why should we give them capacity credits? The only problem is this idea of how much restriction could you constrain this guy 1 megawatt to unlock 100 megawatts? You probably say yes. How do you facilitate that is probably the more pertinent point, right? And to facilitate that, I guess the idea would be we should have master planning body that goes, okay, we could unlock gigawatt of capacity by upgrading this shitty little bit of network. Nobody wants to do it. Why doesn't the government do it, or why doesn't the network service provider do it on their own behest? So there's that idea, like we should just augment the network, or they should just fund augmenting the network. But yeah, I don't think we need network augmentation. So we can't give the impression that everybody can connect and never have to pay for network augmentations, because then who does pay for them?
Well, that's the point I'm making. There's a barrier to achieving the capacity you need. That's
yeah, and I guess processes like
the network. There's a lot
yeah.
of certainty in 5 years as to whether it's going to be around. So it's sufficient levels to meet a load forecast, for instance. So,
And I think the hope is that mechanisms outside this, like the WASP or the ISU or whatever, can draw attention to the fact that there is such a mechanism. This is happening almost at the last minute, at the 2 year in advance, the last point at which we need to commit generators or we won't have enough. So we would hope that this forward-looking planning, this 10-year planning, picks up on the issue and somebody makes a judgment call that somebody, whoever it is, the market participant or the government or whoever, commits to augment that network. But I mean, you can't just not augment it, right? If there wasn't an augmentation, there's probably a reason, it wasn't economical, and there should be a better place for you to connect, and that's what the mechanism wants to do.
Well, that's right. The mechanism really encourages connecting the parts of the network that are constrained.
Absolutely.
When there's no place left.
Yeah, and the other thing to keep in mind here is that this isn't the only source of revenue. Like in many parts of the world, and including the East, you make all your money from the energy market. So whilst we have a capped energy market, you still get money. And so even if you connect in an entirely constrained part of the network and get 1%, 0% NAQ, you're still getting money through the energy market.
Well, that's right, because they're probably located in a better place in terms of where they are relative to those other generators who are getting water capacity credits.
Yes.
They'll be constrained back.
So in real time,
and they'll be actually constrained on. So
yeah.
So they'll make more money in that sense.
So when the objective function in real time is what's cheapest, they get on more often and they might make enough money doing that. And that's okay, because the capacity credits are costed sufficient that it should cover their operating costs and their bank costs for these facilities. So that should be enough even if you never turn on, roughly.
So if you're going to retire something like all of the coal fleet eventually, NAQ's probably going to be a bit too short to figure out if you can or cannot like sort of replace bridge, for instance. So you look at the WASP or the ISU for that.
That's right, yeah.
Because
So I mean, you could do studies with this, like we have. So we have applied this model to, say, NCES, and just to go, oh, hypothetically, let's add 10 more facilities and see what happens. How do they play nice with each other? So you can, but inherently it's not for that. It's to provide the certainty in 2 years. And yeah, if you're looking at what happens if all the coal goes, that's other planning processes.
Yeah, same question from me. With addition to him, we are planning for all coal generation retired, isn't it, for net zero carbon emission. Then we are planning to use our renewable energy system. Now we are further planning for nuclear system. Is it sufficient for this next system fluctuate.
Yeah, there's no problem, because in any year like that event happens, and we've already gone through this with a coal generator retiring in the model.
Yeah.
It just means that suddenly network capacity opens up for somebody else. So somebody new or somebody existing that was being constrained down suddenly gets more capacity credits.
For instance, if I'm not mistaken, in 2016, we had blackout outage concerns on South Australia. So similarly, it may happen in Western Australia. How we have such type of service and protection system or system?
Yeah. Well, so there's a whole world there about reliability and energy modelling, which is touched on in the ISU and the transmission plan. This one is just, do we have enough at our time of most need? Which is one question. It's a big question, but it's not the only question. There's this other idea of the energy duration gap. And that chart I had before about how much credits do we give to our storage facilities is critically important, right? This, oh my god, I'm not sure I'm going to get all the way there. But, hang on.
Oh, we need to go for the first step.
You know which slide was it?
This one. So, that's where this comes in, right?
Yeah.
So if you have been historically certifying all your energy storage facilities for 4 hours, but we transition to a world where we don't have coal and we have limited gas and maybe the nuclear isn't ready yet and everything's done by wind and solar and batteries, this becomes massively important. And you have to decide how much capacity credits are firm and how much capacity credits are storage balanced. Because if it's you need almost all your capacity credits from storage, then they've somehow got to last the whole day. You know, so our 4-hour batteries are now only 10% efficient as they were. So the model will correctly say we have a shortfall and that we need more. However that comes from a new gas turbine, a new nuclear reactor or whatever happens, the model will correctly say, hey, we are really short because our existing energy facilities all of a sudden are now much less helpful than they were. I'll just note though, this idea of changing the 4 hours, this is not in the rules yet. It's more drawing attention to the fact that there needs to be something like this in the mechanism and some way of saying, hey, energy resource, commit to the network. I know that your capacity credits might go down, but we'll guarantee a certain amount or something to make them whole, right? But the idea is we do have to respect reality and try and answer the question of how short are we? How much storage do we need? Can we survive with the people that have applied, right? So it all comes down to this idea.
Thank you.
No worries.
Thank you, everybody. Yeah.
No worries.
Thanks everyone for attending. I think those are the sessions.
Well, we just say thank you to Lucas.
Thank you very much. Cheers. Am I allowed to? Thank you, everybody.
Thank you, everyone.
Cheers.